The sky over Sverdlovsk is an immense and empty canvas, a place of profound silence. On the radar floor of the 4th Independent Air Defense Army, that silence is a threat, a void that must be filled with the patient arithmetic of electromagnetic pulses. The year is 1960, and for 40 years, we have been taught that a legible sky is a controllable sky. A May morning in the Urals smells of thaw and industry. It is the scent of snow beginning to lose its grip, sliding in wet sheets from corrugated factory roofs. It is the sharp tang of diesel in the rail yards and the soft hiss of radiator steam in the concrete courtyards. It is the smell of a nation holding its breath, a nation built on the promise of vigilance. But down here in the dim, climate-controlled heart of our air defense network, we live on a different calendar. Our seasons are not marked by snow or sun, but by the relentless sweep of the radar beam. Our dawns are measured in blips of light on a dark screen, in azimuths and altitudes. On the walls, the maps hang like sacred texts, like prayers rendered in ink and paper. They depict a vast and complex lattice of overlapping arcs, of sectors of responsibility, of missile engagement envelopes. They are an attempt to impose a human geometry onto the boundless expanse of the heavens. They are an article of faith. For my entire life serving in the Protivovozdushnaya Oborona, the PVO, we have been taught to believe in this faith, that what can be mapped can be understood, and what can be understood can be controlled. And then it appears. A single point of light, green on black, pulsing with an insolent, steady heartbeat. It is a contact that should not be there. It violates the sacred geometry of our maps. The initial reports from the operators are tinged with a professional disbelief, a quiet tension that sharpens the air. The altitude estimate comes in 70,000 feet, nearly 14 miles straight up. The speed is high, but it is not the frantic, incandescent velocity of a meteor or a piece of space debris. This object moves with an unruffled steadiness, a calm and deliberate purpose, as if the thin, freezing air at that altitude is a quiet annoyance rather than an absolute physical limit. I am Lieutenant General Yevgeny Savitsky. My life has been forged in the PVO, rising through the long nights of endless drills, memorizing the unique tempers and tantrums of different radar systems, and learning the cold, hard confidence of a launch sequence. I know the rules, I know our doctrine, and our doctrine, the accumulated wisdom of our best minds, states clearly that nothing man can sustain level flight at that altitude for any meaningful length of time. Our best interceptors cannot breathe there. Their wings cannot find purchase in air so thin. Doctrine is a comforting thing. It is a shield against the chaos of the unknown, reducing the infinite possibilities of the world to a set of manageable rules. You learn to trust doctrine, as other men trust old friends or religious faith. It tells you who the enemy is, what your missiles can reach, and how to divide a limitless sky into neat triangles of responsibility. You never, ever suppose that your doctrine might one day be outclassed by a simple act of invention. The ritual begins to unfurl with the precise, practiced choreography we have taught ourselves. There is no panic, only a heightened state of awareness. Technicians, their faces illuminated by the glow of their consoles, run their final checks. Radar operators verify their tracking locks, their voices calm and measured as they call out the coordinates. Across the region, the crews of the S-75 Divina missile batteries prepare to sing their metallic song. The Divina, which the West will later call the SA-2 guideline, is a magnificent thing. It is our doctrine made manifest in metal and fuel. It is a long, thin, elegant instrument of vengeance that we can point directly into the heavens. It is the fist of the PVO. We train with these systems until our hands know the cadence of their firing procedures like a prayer, until the sequence of commands is burned into our muscle memory. The men who operate them are not theorists. They are practitioners of a deadly craft. They are believers in the simple physics of trajectory and explosion. Today, their faith will be tested. The target continues its serene, unhurried path across our territory, a silent rebuke to the very concept of our borders. It is an act of supreme technological arrogance. It flies with the assumption that it cannot be touched, that it exists in a realm beyond our reach. We are about to challenge that assumption. The orders are given, relayed down the chain of command with crisp efficiency. On the ground, in launch sites hidden in the forests and fields around Sverdlovsk, the commands are received. The great white missiles are raised on their launchers, pointing their sharp noses toward the cold, indifferent sky. I give the final order. Fire. The volley is launched. 14 missiles climb into the sky. A lattice of white smoke, intense heat, and unwavering intent. There is a strange, grounded theatricality to a surface-to-air missile launch. It is a moment when all the complex theories of aerodynamics and ballistics, all the political tensions of the Cold War, boil down to a simple, violent trajectory. It is the work of men in thick wool coats and heavy boots, men who understand that for a brief, fiery moment the fate of nations rests on a perfect calculation. We watch on our scopes, our breath held, believing, trusting that the machine will do what the machine was built to do. We believe in our geometry. We believe in our steel. As the 14 streaks of white smoke clawed their way into the stratosphere, the atmosphere on the radar floor was electric. The green blips of the S-75 missiles converged on the single, arrogant pulse of the intruder. For the men watching their screens, time itself seemed to stretch and slow. They were no longer just technicians, they were spectators at a contest between two opposing philosophies of power. One missile, guided by the patient mathematics of our ground controllers, finds its mark. On the scope, the result is a sudden, brilliant bloom of light. The target blip fragments, expands, and then vanishes. A collective, sharp intake of breath fills the room, followed by a low murmur of triumph. Out in the cold, thin air, 70,000 feet above the Ural Mountains, Francis Gary Powers' U-2 spy plane shears apart like tissue paper under the force of an enormous invisible hand. The delicate, high-aspect wings snap. The camera plates containing their granular truths shatter. Fragile instruments, a man in a pressurized suit, a fragile dream of invulnerability, all of it is torn asunder and cast down toward the earth. For a few moments there is nothing but the falling debris, and then the stark, black and white photographs of the wreckage to prove the thing had ever existed at all. The news travels up the chain of command with the speed of a shockwave. Moscow shouts, "Victory!" The Kremlin, usually so guarded and opaque, cannot contain its glee. The shoot-down is a propaganda coup of the highest order. They display the fragments of the U-2 on state television for all the world to see. The twisted metal, the powerful lens of the camera, the survival kit issued to the pilot. In the fleeting, incandescent glow of this triumph, we of the PVO have given our political masters a perfect moment. We have delivered undeniable proof that our skies can be defended, that American arrogance can be met with steel and fire and punished. The international outcry, of course, will be another thing entirely. It will become a storm of diplomatic protests, of United Nations resolutions, of a sheepish presidential apology from Dwight Eisenhower himself. The carefully constructed lies of the American government, that this was merely a weather plane that had strayed off course, will crumble in the face of the undeniable evidence of the wreckage in the captured pilot. But for us, the men of the PVO, the message is far more immediate and personal. We have reached to the very edge of space and torn down an intruder. We have performed flawlessly the exact function for which we were created. Pride, sharp and clean, flows through the ranks. And yet, as the initial euphoria begins to fade, a different kind of absence begins to open up in its place. The U-2 was more than just an aircraft. It was a mirror. For 4 long years, its patient, high-altitude flights had brought the world home to Washington in the form of incredibly detailed photographs. They saw our missile silos being constructed, our shipyards building new submarines, the hangars where our strategic bombers were housed. These images were granular, undeniable truths that allowed their strategists to measure our capabilities and their policymakers to reason with facts rather than with fear. In a strange and paradoxical way, the intelligence gathered by these flights had a calming effect. It replaced the monsters of paranoid fantasy with the knowable dimensions of concrete and steel. These photographs helped to calm parliaments, to set the real terms of arms control debates, and to prevent the febrile logic of brinksmanship from spiraling out of control. With the shoot-down, a new and far more complex problem emerges. The method that bound understanding to evidence, the very tool that kept the worst fears in check, has now been compromised. The United States now needs a new method. They need a new platform, one that will not be vulnerable to the impressive reach of our S-75s. The requirement that flows from this new reality is not only technical, it is a deeply political and strategic imperative. In the inner rooms of the Pentagon and the White House, the brief becomes almost obscene in its ambition. They must build a machine that simply cannot be reached. Not by our missiles, not by our interceptors, not by anything we can throw at it. So our great victory, the moment of our highest achievement, has in fact planted the seed of our next great challenge. The public explanations from the Kremlin will remain raw and bloody and elegant. They will speak of the inviolability of our borders and the strength of our defenses. But in the quieter rooms, among the generals and the technicians who understand the deeper currents of this technological war, we know something else. We know that the shoot-down does not end the problem of aerial espionage. It simply and dramatically changes its character. If they can build a plane that the Divina cannot touch, then our entire air defense network is not just proven to be effective. It is, at the same moment, proven to be insufficient in a new and higher register. We have won a single decisive battle, but in doing so, we may have just instigated a new phase of the war, one that will be fought at altitudes and speeds we can barely imagine. We will need a doctrine that goes beyond mere vertical reach. We will need a new kind of weapon for a new kind of threat. The victory of May 1st, 1960, a date that should be marked by celebration, now feels like a heavy door swinging open onto a dark and uncertain future. The silence in the sky has been broken, but the silence that follows is filled with the unsettling echo of our own success. While we in Sverdlovsk were annotating our maps and reading the triumphant cables from the Kremlin, a very different conversation was taking place thousands of miles away. It was a conversation held not in grand, wood-paneled offices, but in a nondescript hangar at Air Force Plant 42 in Burbank, California. This was the home of a small, secretive team of men and women who swore by two things: the absolute necessity of secrecy and the simple, honest utility of the workbench. This was the Lockheed Advanced Development Projects Division, known to the world, if at all, by its strange, evocative nickname, the Skunk Works. At the center of this ring of pragmatic visionaries sat a man named Clarence Kelly Johnson. He was short, famously precise with his words, and as stubborn as any master craftsman defending his art. He was a man who had built a career on making improbable things not just credible, but operational. From the P-38 Lightning of the Second World War to the F-104 Starfighter, Johnson's designs were known for pushing the very limits of what was considered possible. He had a reputation for cutting through bureaucracy, for demanding the best from his people, and for delivering aircraft that seemed to have arrived from the future. In the wake of the U-2 incident, Kelly Johnson and his team were given a new brief. It was a set of requirements born directly from the political fallout of our S-75 missile volley, a brief that would make most aeronautical engineers smile with a kind of grim, masochistic pleasure. The demand was simple in its articulation and breathtaking in its audacity. The new aircraft had to fly at speeds exceeding Mach 3, more than 2,000 miles per hour. It had to operate at sustained altitudes above 80,000 feet, far beyond the reach of our Divina missiles. It had to carry camera and sensor suites weighing over a ton. It had to be capable of crossing entire oceans and continents. And it had to return with pictures so clear, so undeniable, that they would settle any argument in any briefing room in Washington. In short, they were tasked to build a plane that the Soviet Union simply could not touch. The pure physics of this brief read like a litany of impossible demands. At 80,000 feet, the air is a fundamentally different element. It is so thin that there is not enough oxygen for a typical jet engine's compressors to get a proper bite. The friction of moving through even that thin air at Mach 3 would generate skin temperatures that would melt the face of a conventional airframe. Aluminum, the old and trusted friend of aircraft designers for decades, would lose its structural integrity, soften, and fail catastrophically. The machine they needed to build would have to be made of something else entirely. The solution began not with aerodynamics or engine design, but with a fundamental question of material science. The answer was titanium. This remarkable metal was a dream on paper. It was incredibly strong, highly resistant to heat, and significantly lighter than steel. But in the workshop, it was a nightmare. The challenge of working with titanium on an industrial scale in 1960 was immense. And here, the story takes a turn of delicious historical irony. At that time, the world's best and most plentiful sources of high-quality titanium ore lay deep within the soil of the Soviet Union. The very nation that the new aircraft was designed to spy on was the primary supplier of the exotic metal needed to build it. The Central Intelligence Agency, which was funding the project, was forced to become an unwilling customer of its primary adversary. This led to one of the great clandestine commercial operations of the Cold War. The CIA established a web of front organizations and shell corporations, creating convoluted chains of commerce designed to obscure the final destination of the precious metal. Third-party agents in Europe and around the world would purchase the titanium from Soviet suppliers, supposedly for civilian industrial uses like building chemical plants or desalination facilities. The metal would then be transshipped, rerouted, and quietly delivered to the gates of the Skunk works in Burbank. The very metal that would eventually clothe the ultimate symbol of American technological invulnerability would, for a time, bear a faint, invisible Soviet stamp. The first tools used to build this revolutionary aircraft were not wrenches or rivets, but the quiet, deceptive instruments of international espionage and creative accounting. For Kelly Johnson and his team, the challenge was just beginning. They now had the raw material, but they would soon discover that turning it into an airplane would require a revolution in the art of manufacturing itself. For the machinists and craftsmen at the Skunk Works, the arrival of the first shipments of titanium marked the beginning of a long and frustrating education. Working with this new metal was less a process of manufacturing and more a form of modern alchemy. It was a material that seemed to actively resist being shaped, a metal with a stubborn, unforgiving personality. The men in the Burbank facility were masters of their trade, artisans who had spent their lives shaping aluminum. They knew its tolerances, its weaknesses, its familiar and friendly texture. Aluminum could be drilled, cut, and milled with a soft, predictable confidence. Titanium, however, betrayed that confidence at every turn. It would seize up standard cutting tools, the immense heat and pressure of the friction welding, the tool tip to the metal it was supposed to be shaping. It would gum up with conventional lubricants, creating a messy, unworkable slurry. Drill bits made of the hardest tool steel would shatter against its surface. The initial stages of the project were filled with the sounds of failure, the sharp crack of a broken drill bit, the high-pitched squeal of a seizing lathe, and the quiet, frustrated curses of men who were used to being in complete control of their materials. Kelly Johnson's people quickly realized they could not simply force the titanium to bend to their will. They had to learn its language, to understand its unique properties, and to invent entirely new ways to cajole it into the precise shapes their blueprints demanded. This meant that before they could build the plane, they first had to build the tools. They developed new cutting tools made from exotic, ultra-hard alloys. They experimented with a host of new lubricants and cooling fluids, eventually discovering that for some processes, a simple wash of distilled water was more effective than any complex chemical. They had to retrain an entire generation of machinists, teaching them to work with a slower, more patient rhythm, to listen for the subtle changes in the sound of the cutting tool that signaled it was approaching its breaking point. They learned to coax the metal into tolerances measured in mere microns, a level of precision that was almost unheard of in large-scale airframe construction. Slowly, painstakingly, the raw sheets and heavy plates of titanium began to dawn into something that started to look aerodynamic. The design that emerged from these efforts was unlike anything that had ever flown before. It was a creature of strange, sweeping curves and sharp, threatening angles. The aircraft featured smooth, blended chines, sharp edges running along the sides of the fuselage that were designed to dramatically reduce its radar return. From the front, the aircraft would present a tiny, almost invisible profile to an enemy radar, scattering the electromagnetic pulses away rather than reflecting them back to the receiver. Even the seams of the aircraft were part of a radical new design. Philosophy. The engineers knew that at Mach 3, the skin of the plane would heat up to hundreds of degrees Fahrenheit, causing the titanium to expand by several inches over its entire length. So they designed the fuselage to leak. On the ground, sitting on the tarmac, the panels would fit together loosely. Fuel would literally drip from the seams, pooling beneath the aircraft in shimmering puddles. It was a terrifying sight for any conventional aviator. but it was all part of the plan. Once the aircraft accelerated to cruising speed, the skin would grow hot and expand, and the joints would press together to form a perfect high-integrity seal. The plane was only truly whole when it was in its element, screaming through the upper atmosphere. The craft was a marvel of structural engineering, a fuselage that was also its own fuel tank, a design that was intentionally incomplete at rest, only achieving its final form in the crucible of high-speed flight. It looked as if some visitor from the future had sketched an idea on a napkin, and Kelly Johnson's team had found a way to fold it into solid metal. This was the work that happened far from the public eye, far from the headlines and the state broadcasts. It was the long, slow, difficult work of turning a political necessity into a physical reality. It was the patient craft of the machinist at the lathe, the smell of coolant and hot metal filling the air, as a small, rough scrap of titanium slowly, carefully became a single, perfect flange that would one day sit deep inside an engine that drank volatile fuel and pushed a plane beyond the known limits of the sky. While the artisans at the Skunk works were engaged in their slow, alchemical battle with titanium, another, equally formidable challenge was being tackled in the engine workshops of Pratt & Whitney. An airframe that could withstand the heat of Mach 3 was useless without a power plant that could generate the necessary thrust and, even more critically, survive in that same brutal environment. The brief Kelly Johnson had received was as much a problem of propulsion as it was of metallurgy. No off-the-shelf turbojet engine could meet the demands. A conventional engine, if pushed to operate at Mach 3 for any length of time, would simply melt. The air entering the intake at that speed would be compressed and heated to a temperature that would cause the turbine blades at the front of the engine to soften, stretch, and disintegrate, leading to a catastrophic failure. They needed an engine that was a different kind of animal altogether. The result was the Pratt & Whitney J58, a technological marvel that was, in reality, two engines in one. At lower speeds, during takeoff and acceleration, it functioned as a more or less conventional afterburning turbojet, but as the aircraft climbed and accelerated past Mach 2, the engine began a remarkable transformation. Its heart, it turned out, was as much about compressing shock waves as it was about spinning turbines. The key to this transformation was a large, movable cone known as a spike, located at the front of each engine intake. As the aircraft accelerated, this cone would slide backward, moving up to 26 inches with computer-controlled precision. Its purpose was to manage the supersonic shockwave created by the plane's incredible speed. It would position the shockwave perfectly at the intake's lip, slowing the incoming air to a subsonic speed before it ever reached the engine's compressor faces. At high speed, the J58 worked less like a conventional air pump and more like a carefully tuned series of shock cavities. The cone and the complex system of ducts and bypass doors around it were doing the majority of the compression work, essentially turning the entire intake nacelle into a ramjet. This created an odd, perverse, and brilliant kind of efficiency. The J58 was one of the few engines ever built that actually became more efficient as it accelerated. It learned to breathe better, to thrive in the very conditions that would destroy any other power plant. It was an engine that rewarded a daring hand on the throttle. This revolutionary engine, of course, required a revolutionary kind of fuel. Ordinary jet fuel, a refined form of kerosene, was far too volatile. It would boil and detonate in the extreme heat and low pressure of the upper atmosphere. So a new fuel was developed. Designated JP7, it was a sluggish, stable, almost oily slurry with a very high flash point, meaning it would not ignite easily. It was so stable, in fact, that you could drop a lit match into a bucket of it and the flame would be extinguished. This made it safe, but it also created a new problem. How do you light a fuel that is designed not to burn? The answer was as dramatic as the aircraft itself. To start the engines and to light the afterburners, a small amount of a chemical called triethylborane, or TEB, was injected into the combustion chamber. TAB is a hypergolic compound, meaning it bursts into flame spontaneously and violently the instant it comes into contact with oxygen. Each time the pilot needed to light the fires, a small charge of TEB would be injected, creating a brilliant, almost supernatural green flash that would ignite the stable JP7. The aircraft didn't just fly, it was brought to life by a kiss of green fire. The entire program was given the code name Archangel, a fitting name for a craft that was designed to operate in the heavens, far above the reach of mortal men. The aircraft that finally emerged from the Skunk works was black and long and utterly improbable. The first versions, the A-12s built for the CIA, were the sleek, dangerous embryos of what would later become the more famous SR-71 Blackbird. It was a machine that seemed to have been designed by a different species. Its long fuselage was also its fuel tank. It was designed to leak on the ground, only sealing itself in the fiery glow of flight. On our Soviet radars, the thing would register as a faint, ghostly whisper if it registered at all. Its unique shape, its Chinese, and its special radar-absorbent black paint were all designed to scatter and absorb radar returns. Its heat signature, while immense, was carefully managed by the design of its engine nacelles. It would fly not like a plane, but like a ghost, a phantom streaking across the roof of the world. It was the physical manifestation of an idea, a machine built to answer a single political question, a question posed by the success of our own S-75 missiles on that May morning in 1960. Back in Sverdlovsk and in the high commands of the PVO across the Soviet Union, we did what we knew how to do. We trained our men to intercept the threats we understood using the tools we already had. But as the first intelligence reports about the Archangel program began to filter in, a cold realization dawned. Our existing tools were no longer sufficient. The S-75 Divina, the hero of 1960, was a magnificent weapon, but it had a ceiling. The new American machine was being designed specifically to fly above that ceiling. We needed a new answer. The Mikoyan-Gurevich Design Bureau was tasked with providing that answer. The result was an aircraft that was, in its own way, as extreme and as remarkable as the Blackbird. It was called the MiG-25. In the West, it would be given the NATO reporting name Foxbat, a name that conveyed a sense of predatory cunning. But the aircraft itself was less about cunning and more about raw, unadulterated power. The MiG-25 was not an elegant balance of advanced avionics and refined control systems. It was a machine built by a culture that deeply understood and deeply trusted the logic of brute physics. If you cannot master the complexities of machining titanium on a mass scale, you build with what you know, heat-resistant nickel-steel alloy. If you cannot develop complex, miniaturized electronics, you build with powerful, robust, and heavy vacuum tubes. And if you need to get to an extreme altitude in a hurry, you bolt on the two largest and most powerful engines you can possibly design. The Foxbat was a verticality machine. It was designed with one primary purpose in mind: to climb like a stone thrown upwards by a giant, to reach an extreme altitude as quickly as possible, and to launch massive air-to-air missiles at a target that was flying straight and level. Its radar was enormous and incredibly powerful, so powerful that it was rumored it could burn through enemy jamming and could, from the ground, kill a rabbit at a range of a mile. It was paired with huge R-40 missiles, each one nearly 20 feet long. The Foxbat would not be nimble, it would not win a dogfight, but it was designed to get high, fast, in a way that just might matter. And so began the long, frustrating chase. Across the northern sectors, over the Barents Sea, along the peripheries of our airspace, we would get a fleeting whisper of a contact on our early warning radars. A faint track moving at a speed and altitude that defied belief. The alert would sound and the scramble order would be given. Our MiG-25 pilots would strap themselves into their cockpits, feeling the immense G-forces build like a physical prayer as they climbed in almost vertical profiles, their afterburners tearing a hole in the sky. Their mission was always a desperate hope: to sneak into a firing corridor, to get just close enough, for just long enough to get a radar lock and launch their enormous missiles. But the fundamental geometry of the problem was always against us. The Blackbird was not just high, it was fast, impossibly fast. By the time one of our Foxbats had clawed its way up to 80,000 feet, near touching the edge of the Blackbird's passage, the American aircraft was already tens of miles downrange, its mission cameras having already captured what they came for. The SR-71's mission was complete, its photographic plates filled with images that would soon be unloaded, developed, and poured into the briefcases of men who made policy in Washington. For our pilots, the experience was one of profound frustration. They were pushing their machines and their own bodies to the absolute limit, only to arrive a few minutes too late, staring at an empty patch of sky. They were chasing a ghost, and the ghost was always faster. This dynamic highlighted a deeper truth that the operator on a radar floor or the pilot in his cockpit rarely considers. Mastery of the sky is not just a function of powerful thrusters and advanced metallurgy. It is a function of an entire culture of systems and networks. It is a doctrine embedded in sensors, in fuel logistics, in global communications, and in theater-level planning. The Blackbird did not fly alone. It was the tip of a very long and very sophisticated spear. Its missions required a fleet of specialized KC-135Q tankers, flying precise orbits over friendly territory, ready to offload the unique JP-7 fuel to feed the Blackbird's hungry J-58 engines. It required pilots who would breathe pure oxygen for hours before a flight to purge their blood of nitrogen, who would don full-body pressurized suits like astronauts, and who would calmly accept that the multi-million-dollar plane they were flying would leak fuel all over the ramp until heat sealed it in flight. It was the product of a society that was able to move vast sums of money and dedicate its best minds in quiet rooms to the single-minded pursuit of technological dominance. We could build a taller ladder with the Foxbat, but they had built a machine that simply flew over the wall. For years, the MiG-25 Foxbat remained a specter in the minds of Western intelligence analysts. They saw its massive wings and colossal engine intakes in satellite photographs and knew it was capable of incredible speed. They extrapolated from its size and power, creating a myth of a superfighter, a machine that could outrun and outclimb anything in the American arsenal. In some Western pamphlets and intelligence briefings, the Foxbat was conjured into a terror, a symbol of a Soviet technological leap that threatened to upset the delicate balance of power. Then, in September of 1976, another thread wove itself through this long and complex story. A Soviet pilot, Viktor Belenko, disillusioned with the system, flew his MiG-25 from a base in Siberia, descended to low altitude to evade our own radars, and landed at a civilian airport in Hakodate, Japan. He delivered into the hands of the West the one thing they had never had, a complete, fully intact Foxbat. The inspection that followed, conducted by American and Japanese engineers, was a profound unmasking. The Foxbat, it turned out, was not the conjured terror they had imagined. It was, without question, a marvel of raw capability, a masterpiece of brute force engineering. But it was also a perfect demonstration of Soviet priorities and limitations. It was built largely of steel, not titanium. Its avionics were built around powerful but primitive vacuum tubes, not sophisticated solid-state electronics. It was a machine designed for performance and survivability, with finesse and refinement being distant secondary concerns. When Western engineers pried open the Foxbat's panels, the result was not the collapse of fear, but a dawning recognition. They realized that technology speaks in languages that are both technical and cultural. The Foxbat was a reflection of the Soviet system itself. Powerful, direct, suspicious of overcomplexity, and willing to accept trade-offs in elegance to achieve a raw, undeniable capability. What the Americans could do with subtle, complex electronics, we could do with a bigger engine and a more powerful radar. Both approaches had their own logic and both had consequences. The Blackbird, the Foxbat, the S-75 Divina, all of these machines existed in the same harsh dialect of Cold War practicality. Each was born of a specific fear and nurtured by immense resources. Each was a response, a move in a deadly, high-stakes conversation. Each, in turn, rearranged the assumptions of the other. When one side learned to see farther and higher, the other side had no choice but to build a longer knife or a thicker shield. Seeing begets adaptation, and adaptation begets the next generation of secrecy and invention. Looking back now from an office that has seen both the sharp thrill of triumph and the slow, grinding erosion of certainties, that May morning in 1960 still hangs in my memory as a pivot. We proved our reach, we shot down a spy and shattered a nation's pretense of invulnerability. But we also learned the hard, unforgiving truth that a technological victory often produces an answer from the other side that is even more difficult to counter. My men in the PVO learned to calibrate their pride, to understand that our victory on a single day did not mean the future would be kind to our doctrine. Men like Kelly Johnson, working in secret on their Black projects, understood the world differently. For them, the problem was a machine and a production line, a matter of geometry, metallurgy, fuel chemistry, and manufacturing schedules. They took a political necessity and turned it into the tangible reality of metal and fire. For us, the Savitskys and the commanders of the PVO, the problem felt more like a test of faith. Had we built a mighty fortress only to be outflanked by a new kind of craft that could simply fly over our walls? We had shot down one intruder, they had responded by building a better one, and so the cycle would continue. The SR-71 retired in the 1990s, its role largely replaced by the even higher gaze of reconnaissance satellites. The world had changed again, yet the lesson of the Blackbird and of our futile chase remains. The Cold War was not decided by one dawn or one missile. It was decided by an accumulation of small, merciless, and brilliant adjustments as altitudes were pushed, engines improved, and doctrines rewritten. We learned that the sky does not belong to the man who can simply shoot. It belongs to the man who can see, and to the society that can build the tools to make that sight matter. On May 1st, 1960, a radar floor went quiet, not because the action was over, but because what had just happened had fundamentally changed the grammar of the conflict. We had spoken with heat and iron, the other side had answered with speed and alchemy. The lesson is plain, powerful, and deeply unromantic. In the long wars of machines, we are always just one step behind the machines we do not yet understand. The rest is simply history, painful, incremental, and deeply, undeniably human.